So next we'll check out the quality of the calibration using our PicoVNA check standard. This is a mismatched 25 ohm line between the two 50 ohm SMA connectors there, a precision stable mismatched line, and this makes a very good check of or a very comprehensive check of our VNA calibration, because this has to be measured very accurately in the presence of its own very substantial mismatch, and so this is a very good test as to whether the ports of the VNA have been calibrated well. Let's remove the eCal module. And fit the check standard. There we are, and there's our measurement. And let me show you here. We have a mismatch characteristic that starts at good match, comes to bad match, good match, bad match, good match, bad match. So as we look right across the frequency span, we are presenting our VNA with both good and bad match that is constantly varying, and therefore causing a very substantial problem to a miscalibrated VNA. This is the transmission characteristic from port 1 to port 2. You can see it's a small loss that we're seeing along the line, and we're looking at that in quite substantial detail here. I'm at half a dB per division. This is the phase characteristic along the line, and here's the mismatch on port 2 shown as a Smith chart. We know what this check standard should measure, because the check standard comes with traceable measurement data from its own calibration, and so this measurement should match within the specification of the VNA. This measurement should match its own data. So let's load that data. And there you are. I'm now displaying behind the plotted data, or the measurement. We are now plotting the true data for this check standard, and of course it's very difficult to see it, and I'm very glad of that. I can see some small perturbations here around 5 gigahertz. We have a utility that can help us make a comparison of the two. With this utility, the compare data utility, we select the file holding the specification or the uncertainties for this instrument, and that is, I'm going to use this instrument uncertainty. It's a PicoVNA 108. I'm using premium calibration leads and adapters here, so PC 3.5. Now I will say the check standard and the eCal module both have SMAs on them. So there is a strong argument that I should be using this uncertainty, because whenever there's an SMA in the system, we should be using a slightly looser specification for the measurement. But I am very happy that these are very high quality SMAs, and I want to show you the performance to the best degree I can. So here we go. I'm going to use this uncertainty, which is the tightest. So we'll open that, and we're also going to open the uncertainty of the reference for the measurement of the check standard. And this is done in a first tier arrangement, directly traceable to the National Physics Laboratory. So that data came with the check standard. Open, and we're going to compare. Oh, by the way, I am excluding the reference uncertainty here. Compare, and you can see at the top here I've got a past result, and here I've got a display of all the S parameters for the check standard in a long list, and passing every point, as you can see. Let's get those results saved. And we'll get those plotted for you, so we can see just how good that calibration was. So for the 4 S parameters, reflection on the left and transmission on the right, these plots are for the data that we saved from the compare data utility. What we've plotted here is the reference data with the measurement specification bounds, or the measurement specification uncertainty. The uncertainty around the magnitude, so we see a grey line with a grey band around it, and for phase it's an orange line with a yellow band of uncertainty around it. So the shaded sections, we expect our measurement to lie within if we meet specification. And in fact, if it didn't meet specification, little red crosses would appear where the measurement fails to meet its bounds. And so you can see we are inside specification, but it is a little bit difficult to see at this magnification just how far. So to get a view as to how well we sit within specification, what we plot is the measured data within normalized specification bands. So on the left here I've got my reflection parameters plotted for magnitude and phase within the spec bounds. And this data on the left is from the automated eCal that I performed, and on the right I've done exactly the same process. I present the data for the manual calibration that I performed. Now you can see that both sit well within specification, and I'm very glad of that. Frankly, I think all of us would have liked the manual calibration that we perform to have beaten the automated calibration hands down, but that certainly isn't the case here. These two measurements, based on automated eCal and manual cal, are very similarly placed within their specification bounds, and it's the same specification in both cases. Looking at the transmission parameters, I think I'd argue that the manual calibration did a little bit better here, but the eCal is also within specification. And if you recall, we used the PC 3.5 uncertainties, and we chose to ignore, i.e. set to 0, the reference measurement and stability uncertainty. In other words, we are meeting the best instrument specification, assuming no SMAs are in use, and that our reference data is absolutely perfect. So what we have here is both calibrations readily meeting the tightest specification that we can apply, and very little difference between the calibration methods. Okay, so that was a fairly compelling demonstration of the quality of the e-calibration against a manual calibration. But we should go a little bit further. When we make one of these a manual fixed calibration piece, we can realize a fairly good short simply by placing a hard short at the end of a transmission line inside the device here. Likewise, we can realize a fairly good open by putting a low capacitance, low fringing and low capacitance open at the end of a transmission line in here. And we can also make a fairly good load. And obviously that adapter, precision made, can be a very good through. So we're very happy that when we calibrate with these, we've got very highly reflective ports, very well matched port, and a very good through, very well matched as well. Now, an eCal module is slightly less good. An eCal module has these switches internally, and the switches will add inductance, capacitance, impedance in series with the hard short, the hard the good quality open and the good quality load. So these are not quite so ideal in terms of calibrating the complete area of a Smith chart. We're not reaching with our cal standard the very center of the Smith chart, and we're not perhaps reaching the periphery of the Smith chart with our open and our short. So the calibration one might expect to be slightly less good when we're measuring at the periphery and the dead center of the Smith chart, when we're measuring a very good match, a very good through, or highly reflective shorts, opens, or low impedances, or very high impedances. So I'm going to do a comparison there as well, and I'm going to do that with another very well-known calibration kit. I mean well-known in terms of their traceability back to national standards. This is a very well-known open and a very well-known short, the red one, open the green one. I've got a very good through, and we'll now use these in our measurements to look a little bit further at the quality of the e-calibration relative to the manual calibration, and both relative to the specification of the instrument. Okay, so let's remove the check standard. Will fit the short to port 1, and we'll fit the open to port 2. Just knocking the set apart here, and therefore we have no connection. We're not going to see any transmission, significant transmission from port 1, port 2, or vice versa. So we're only going to be looking at 2 S parameters here. Let's get those torqued up properly, because we are making some pretty good measurements here. Ah. Okay, let's have a look at that. What have we got? Well, let's turn off that reference trace and let's bring this to a slightly higher sensitivity. That'll do. And what you're doing here, and it's this 1-2 phase. Well, we've got no through transmission, so phase plot. And then you can see I've got I'm right round the Smith chart here with that short. Oh, sorry, this will be the open, the S22. Well, we can do exactly the same as we did with the check standard. We can use the compare data utility. We can take the data that was provided with the calibration pieces, and we can compare that with the measurements that we're making here. And this is what we get. So here we have the 2 S parameter plots. We have the short on the left, S11, and on the right we have the open plotted alongside its reference. We can easily see magnitude of reflection, blue, matching very well to the reference data, the grey trace. Certainly well within specification, the light grey shading. Phase is also in spec because there are no red crosses on these plots, but let's look against normalized reference and spec to see how well they actually match. Well, very good match indeed. Phase as well. So again, we have eCal on the left, and on the right, manual cal is an even better match to its own reference. But both are very well within our specification, even though we used the PC 3.5 uncertainty. We can begin to wonder whether any competitor AutoCal solution would anywhere near match this. And then, as I said earlier, we want to measure the through as well. What the through is going to give us is a very good match in the center of the Smith chart. It's going to be a measure of the match of both the adapter and of the correction of the VNA, so the residual match of the VNA. So let's remove these 2 pieces here. Open. Short, and let's fit them through. Now, I'm going to be honest with you, this through is not marked. It's not marked in the sense of the polarity that was used with when it was calibrated. So the data I have for this through, it's uncertain what the polarity is. So in practice here, I have to make 2 measurements and then compare the best ones, which we would deem to be when I've got the polarity of my data and the polarity of the reference data the same. So that's what I do in practice. But now let's have a look at that. And we're going to need something like 10.0 in there. We've got a very good match look, that minus 50 dB rises up to something just below about minus 30 dB. S21, we need something like 0.05. Oops, there. There's my loss characteristic. My phase characteristic, in phase to begin with and sliding away. And then, as we said, our expected very good match in the centre of the Smith chart there. Again, we can do a comparison of data. Well, through being a two-port device, we have all four S parameters again, reflection on the left and transmission on the right. Now, at better than minus 30 dB reflection in both of these plots, we are below our lowest specification band, so there's no shading to meet on the left hand side here. Looking to the right hand transmission plots, you can see that the small transmission loss is very accurately matching its reference data in the measurement here, and is very well within specification. Despite not having a spec in reality, let's look at the comparison of eCal and manual cal on the reflection parameters. Manual cal does win here, but really not by very much. And for the transmission parameters, well, much of a muchness, we would say. A pretty well balanced situation when we compare eCal with manual cal and compare both with specification. So I think the check standard alone gave us a great deal of confidence in the eCal calibration quality. And then by going that little bit further, the short, the open and the through verifications must surely extend our confidence right across the S parameter vector space. I'm impressed. I hope you are too.